Students, I am going to discuss about the use of wind tunnel for making model studies. This picture shows a wind tunnel. A fan is fitted on the other end of the wind tunnel. When the fan is rotated, air is sucked inside through this opening, and this is the test section. The air flowing over the test section will be uniform in velocity, and the air is going out on the other end of the wind tunnel. The test section is shown in this picture. Any model whose lift and drag characteristics are to be found out can be fitted inside the wind tunnel, inside the test section for analyzing. In this example, a aerofoil model is kept inside the test section. This is the close-up view of the aerofoil model. The aerofoil model is fitted for the purpose of analyzing the lift force generated by the aerofoil. Schematic sketch of the aerofoil is shown in this figure. The lift is created on the aerofoil because of the pressure difference of air between the top surface and bottom surface of the aerofoil. In order to determine the pressure acting on each and every point over the aerofoil, there are 12 points, pressure trapping points are drilled over and below the aerofoil, and the pressure prevailing at each and every point is recorded using a manometer. These 12 pressure tapping points are connected to the manometer bank using the hoses. So these tubes that are connected to the pressure tapping point are taken to the manometer bank, and it is connected to 12 number of manometers on this setup. The last manometer is open to atmosphere, which records the atmospheric pressure. On this test section, we have to find the velocity of the air and as well as the free stream pressure of the air. For recording the free stream pressure, a pressure tapping point is fitted on the outer wall of the test section, and a hose is connected and it is taken to this manometer. So this is the manometer that used to record the free stream pressure. So one end of the manometer is open to atmosphere, the other end is taken to the test section. So HF is the reading recorded on this manometer, which is having water as the manometer fluid. So HF is the water level difference on this manometer. To determine the velocity of air flowing over the test section, we have fitted a pitot static tube, which is shown here. The pitot static tube is recording the velocity of air flowing in the test section. The two end of the pitot static tube is connected to a U-tube manometer as shown here. Now the U-tube manometer is filled with water, and the velocity is recorded using this manometer in the form of height difference between the two levels of water level in the manometer. The aerofoil which is used for this experiment is NACA 0018, which is a symmetrical aerofoil, and for the purpose of determining the pressure prevailing at each and every point, there are 12 pressure tappings drilled over the aerofoil as already discussed, and point number 1 is the pressure tapping point drilled at the tail end of the aerofoil. 2, 3, 4, 5, 6 are drilled on the top surface of the aerofoil, and 7 is drilled at the front center of the aerofoil, and point number 8, 9, 10, 11, 12 are drilled on the bottom surface of the aerofoil. So 2 and 12 are on the same vertical line, and pressure tapping point 3 and 11 are drilled on the same vertical line. Similarly 4 and 10 and 5 and 9 and 6 and 8. We need to find the pressure coefficient acting at each and every point over the aerofoil. Here we have drilled 12 number of pressure tapping points. So we have to find the pressure coefficient at 12 points over the aerofoil. The formula to be used is shown here. So Cp at ith point, pressure coefficient at ith point is given by static pressure of air at ith point minus free stream pressure divided by half into rho of air into square of the velocity of air. So these are the nomenclature. To find the static pressure at each and every point over the aerofoil, we are using this formula, rho GH. So since the manometer used to determine the static pressure is filled with the water, so rho of water into G into the height difference. Let me show it. Okay, let us say for example, I want to find out the static pressure at the 12th point over the airfoil. So we have to refer to the reading shown by the 12th manometer. So this is the 12th manometer. So the water level on the 12th manometer is to be recorded, that is H12, and it should be compared with water level on the manometer regarding the atmospheric pressure. So that is taken as HATM. So like that we have to determine for all the 12 point over the aerofoil. So there are 12 manometers which are fitted to each and every pressure tapping point over the aerofoil, and the last manometer is recording the atmospheric pressure. So the static pressure at the 12th point is given by rho of water into G into H12 minus HATM. We need to find the free stream pressure using this formula. Pf is equal to rho of water into G into Hf, where Hf is the reading shown by this manometer that is recording the free stream pressure. So once we know the static pressure at each and every point and the free stream pressure acting on the test section, next we have to determine the velocity of air using the pitot static tube. So the reading shown by the manometer conduct to the pitot static tube is H. So that is already shown. So now this manometer is connected to the pitot static tube. So this reading is taken as H. So once we know the value of H, we have to use this formula. Velocity U0 is given by square root of rho m by rho minus 1 into 2gh. Rho m is the density of manometric fluid. Here what is the manometric fluid? So density of water we have to substitute. Divided by rho is the density of air, which is the flowing fluid. H is the reading shown by the manometer regarding the velocity. So U0 can be found out using this formula. Once you know these three values, you can substitute in this formula to determine the pressure coefficient at ith point. So like that we have to find the pressure coefficient on all the 12 points for this example. Once you know the pressure coefficient, we can draw a graph like this. So now we have to draw a graph between pressure tapping point on the x-axis and pressure coefficient on the y-axis. Now this manometer model is drilled with the 12 number of pressure tapping point. On the x-axis, we are going to show all the 12 points, okay, with the 1:1 scale. So for example, the 6th point is at a distance of 10 centimeter. So from the origin, we have to mark a line for 10 centimeter denoting pressure tapping point 6. Similarly, 8 is also on the same distance. So 6 and 8 are on the same line, 5 and 9 on the same line, 4 and 10 on the same line, 3 and 11 on the same line, and 2 and 12 on the same line. First pressure tapping point is at a distance of 160 centimeter from the origin. So we have to mark all the point in the 1:1 scale. The y-axis is the pressure coefficient. We are going to mark the pressure coefficient with regard to all the 12 points. Then we are going to draw a curve joining point number 2, 3, 4, 5, 6. So these pressure tapping points are on the top side of the aerofoil. So this blue color line shows curve drawn joining the pressure coefficient with regard to the point number 6, 5, 4, 3, 2. Similarly, another curve is drawn. Point number 8, 9, 10, 11, 12 are joined together, and a curve is drawn joining these points. Another curve is drawn joining these points, and the area between the two curves is the approximate value of lift force generated by the aerofoil.